So here's where it starts to get interesting. Maybe not in the first one, but pretty soon after. We'll take a look here. So find the limit of a rational function. Now we have some interesting things to do. Number one is always going to be substitution. Yes. So let's do that. So if I plug in 1, I would get 1 squared, which is 1, plus 2, all over 1 plus 1, which is 2. And the whole thing's going to be what? 4 over 2, which is 2. All right. No big deal there. If you were to graph this thing, you would see it's just fine. Everything meets at 2. There's no gap. Everything's great. Let's see what number 2 does, though. Can you see this coming? If I put in 1, what do I get? Well, I get 1 minus 1 in the numerator and 1 minus 1 in the denominator. So you're going to see I'm going to be very careful. AP is pretty picky about this. That is not equal to 0 over 0. That is just what the value would be at 1. There's a 0 on top, 0 on the bottom. So I'm very careful to put an arrow there, not an equal sign. So here's what we're going to do, though. What has just happened? Do you recall if you guys did this back in pre-calculus? I wonder if you guys did this. If you're looking at this in college algebra trig, sorry, all the names have changed throughout the years. If you were to see 0 over 0, first of all, I challenge you to ask Siri if you've never experienced this awesome discovery. Ask Siri what's 0 divided by 0 and get back to me on that one. Anyway, if you get 0 over 0, that's actually caused by a hole in the graph. There's a hole in the graph. So what we know is if there's a hole, as you saw already, even if there's a hole, the limit still exists as long as it approaches the same value. So let's go ahead and try something here. I'm going to go ahead and play with this thing a little bit algebraically because I see maybe we can factor something. Do you remember your cube? Well, the good news is since there's a hole, this is the beauty. We can actually use some things to our advantage. That says there's x minus 1 in the bottom, so I'll bet anything the hole is at x equals 1. So I'm going to say x equals 1. Oh, sorry, my phone's going off. Just a minute. Shut that off. There we go. Sorry about that. Okay, so if you have x equals 1 is the hole, then we know that x minus 1 is one of the factors because it's got to cancel. If there's a hole and we're trying to get rid of it, that's what we're trying to do. So it's kind of nice. So if you have a pretty ugly one to factor and you know where the hole is, you already know what one of the factors is. All right, so if you recall doing your cubics, well, we can just kind of reason this one out actually. If you need x times something to be x cubed would be x squared. If you need -1 times something to be -1, that would be a +1. The only part you had to memorize, and my students did this all the time, you just remember the middle term as the two numbers in the first factor combined as a product, so it's just x. And then you just know that you only get one minus sign. We already used it, so it's plus and plus. There we go. So look what just happened. X minus 1 reduces. Our hole has been eliminated. So we'll talk about that later. It's called removable discontinuity. We just got rid of the hole. Now if you plug in 1, we eliminated the hole, so there's no problems here. Let's see what happens. Well, that's 1 squared plus 1, which is just a big old 3. And that's all we had to do. So if you were to go to graph this thing, feel free to do that. Go ahead and graph this thing and see what happens. See what the graph does at 1. If you zoom in with Desmos, or if you just do a point check with your graphing calculator, you'll see there is a hole. But on the either side of that hole, it approaches 3. All right, we got one more here, and this is where it gets pretty dang cool. Now, you might recall, I'm trying to remember when this came up. I know I taught it in Algebra 2, so maybe in your Algebra 2 class, maybe you did some in College Algebra Trig last year. We never like to have radicals in the denominator. Well, I have some good news for you. We don't care anymore. That's just fine to have a radical in the denominator. I know some teachers think that's sacrilegious and awful, but it really isn't. We're looking for solutions. We're looking for values that make this thing true. But here's the cool part. We don't want radicals in this for another reason. Let's see what happens. I don't know what. Okay. So if I put in 0, what do I get up top? In the numerator, I get 0 plus 1, square rooted, which is 1, minus 1, which is 0. Ooh, you see that coming? It's 0 over 0. Very interesting. 0 over 0, which means there is a hole. Can you tell where the hole is located? I hope you can. It's at 0, because whatever made the denominator and the numerator, whatever made those, what values would they become? 0. So what would make them 0? If x is 0, there you go. So we know there's a hole at 0. So if we can eliminate that hole, we can find the limit. But here's the problem. I can't factor that top. That's a radical. So here's where we're going to go with that. I'm going to do it in a different color. Maybe I'll just rewrite it. Limit as x approaches 0. And anytime you do another limit in your steps, this is a word of warning for you. If you don't write the limit, sometimes they take off for that, and I will be doing the same thing. Not every single time, but you want to remember, if you haven't taken the limit yet, the limit's still there. So I got to have that limit as x approaches 0. So here's what I'm going to do. If you recall back when you were doing getting rid of radicals in the denominator as it used to be, we don't care where they are now. It's just if there's a hole, we're trying to eliminate it. We are going to rationalize. We're going to rationalize, in this case, the numerator, but here's what we're going to do. We're going to use the conjugate. Do you remember that one? The conjugate. So I'm going to multiply the top and bottom by the conjugate. And how do I know which one to use? Whichever one had the radical. That's the one we're trying to eliminate. So it's root x plus 1, but to get rid of the minus 1 with the root x plus 1, we'll do it times root x plus 1 plus 1. And we'll do the same thing, top and bottom. Now here's the interesting part. It's no harm, no foul, but it does cause a lot of work, so I'm trying to save you the trouble. Our goal is to get rid of that radical in the numerator, because that's just where it was. Do not catch yourself distributing the non-radical piece. So the denominator really doesn't need to be simplified by distributing the x. I'll show you why in a minute. It's pretty cool. So if I distribute that root x plus 1 minus 1 with the root x plus 1 plus 1, we would get, of course, just x plus 1. The middle two terms would cancel because it's an a plus b times an a minus b, and minus 1. On the bottom, we have x, and I'll keep the colors just so we can see what's going on. Root x plus 1 plus 1. All right, so what happens here? Remember, the goal was to eliminate the hole. Well, up top, we got x plus 1 minus 1, which is just x. And what just happened? The x is reduced, so the top is 1. Now, with the hole removed, you see why I didn't distribute on the bottom. With the hole removed, just plug in the 0. So on top is 1, on the bottom is what? Root x plus 1, which is 0 plus 1. And that's 1 after you square root, and that's 2 when you're done. Again, feel free to graph this once you can see what really happened. A lot of times it's good to see the big picture graphically as well as analytically like we're working on today. So that's what we've got today. I hope this is making some sense for you. We'll get plenty of practice with this. And if you have any questions, come see me during my office hours before school or after school, 30 minutes before and 30 minutes after. During seminar, and of course, if class is still going, come back into WebEx and we'll talk there. All right, thanks a lot. Have a good one.